Hello, this is Dr. James Camp from Lee College, and welcome to my lecture on chemistry basics for biology students. This is going to be a stripped down version of chemistry that is basically all you ever need to know about chemistry 1 in 20 minutes or so. All right, first let's talk about the structure of an atom. This is a topic that most people have encountered at some point in their life, but I want to go over it. In the center of every atom is a nucleus. The nucleus contains some number of protons, which we abbreviate P, and some number of neutrons, which we abbreviate N. Protons have a positive charge. You would think that this would push them away, since in electrical charges opposites attract and similars push away. But there are other forces, something called the strong nuclear force, that holds the nucleus together. There are also other forces, such as the weak nuclear force, that tend to drive nuclei apart, resulting in radioactive decay. But we don't need to know all of that for right now. Neutrons are, well, neutral. That's where they get the word neutron. Bad chemistry joke of the day number 1. A proton and a neutron are settling up their charges at the bar. The proton pays up and walks out. The neutron reaches for his wallet and the bartender says, "For you, no charge." Okay. Around the nucleus is what we refer to as an electron cloud. It's called an electron cloud because the electrons don't stay put. The electrons are constantly vibrating and spinning and moving around, orbiting the nucleus. And unlike the atoms orbiting, unlike the planets orbiting the sun, the electrons do not travel in nice, predictable paths. They wobble and spin and weave. And so an electron's path around the nucleus is kind of fuzzy and forms something that looks like a cloud. But it's hard to visualize a cloud. So what we tend to do then is describe the electron movements in terms of discrete shells that have contain electrons in particular positions. Okay. Those electrons actually, for reasons of spin, tend to occupy the electron shells in pairs. Okay, you have an up-spinning electron and a down-spinning electron, if you will, that pair up. Okay, the first electron shell gets 2 electrons. The next electron shell gets 8. The next electron shell gets 8 more. I call this the 2-8-8 rule. Okay, and it looks like an area code, 288, like you could dial that and get some city in America. But it's the number of electrons in the first shell, the second shell, and the third shell. After that, things get weird.
Administrators, meet me in the cabin.
After 2, 8, and 8, things get weird. Their relationship status on Facebook is it's complicated. So we're not going to go any further than 2, 8, and 8 because that's actually all we need for biology. Okay, so that's the structure of an atom. Note a couple of things here. The number of neutrons in my hypothetical atom here is equal to the number of protons. That doesn't have to be true, but they're usually fairly close. You're usually only off by 1 or 2. The number of electrons in my hypothetical atom here are equal to the number of protons. That does have to be true, except when it doesn't. We'll get into the cases where it doesn't in a future slide. But for right now, imagine that the number of electrons is always equal to the number of protons. Okay, so how do you know how many of which things an atom has? The answer is there's a nifty little table of all of that stuff called the periodic table. Periodic table is made up of a series of squares that all look something like this. Okay, there's a symbol in the middle. We'll say that this one is O. Okay, O is the chemical symbol for oxygen. Sometimes the whole word will be written out. Sometimes the periodic table is too small to allow all the words to be written out, so they just have the symbols. Oxygen is an element. An element is a chemical entity that always has the same chemical behavior. And the reason it always has the same chemical behavior is that every oxygen atom has the same number of protons. How do we know the number of protons? Well, I'm glad you asked. There's usually a number either right above the letter O, or maybe it's over here in the corner, but a big number that indicates this is what's called the atomic number. And it equals the number of protons, which I'll call P. Okay, so if we try to draw a little oxygen atom over here, we'd have to put 1, 2, 3, 4, 5, 6, 7, 8 protons in it. Okay, because we know that for oxygen, the atomic number equals P equals 8. And every oxygen atom will always have 8 protons. If you change the number of protons, you have magically turned oxygen into something else. You haven't made a special kind of oxygen. Okay, what about neutrons? Well, there's another number down here that'll be written like 15.999. Okay, this is called the atomic weight. And it is the average weight of every oxygen atom in the world. Okay? Can we have an actual atom with 15.999 weight? No, because this is approximately equal to a number called the atomic mass, which equals protons plus neutrons. Okay. Now, the atomic mass of a typical oxygen atom, the most common oxygen atom, the most stable isotope you can get by rounding this 15.99 off to the closest whole number, which would be 16. So 16 equals P plus N. We happen to know that P is 8 because we just figured that out up here. So what is N? Your basic algebra here, 16 equals 8 plus N. So you subtract 8 from each side and you get 8 equals N. Okay? So if we wanted to draw our oxygen atom over here, we'd have to put in 1, 2, 3, 4, 5, 6, 7, 8 neutrons. Forgot to put my pluses on my protons here. Okay. Now, how do we know how many electrons we have? Well, we said on the previous slide that you can just assume that the number of electrons equals the number of protons. But why is that? Well, there's one more important thing to know about every atom. It has an atomic number, an atomic weight, and it also has a charge. Okay? The charge, if it had one, would be written in this blue circle right here above the chemical symbol, the letter O. There isn't one, so we know that the charge is neutral or 0. Okay. Charge is equal to the number of protons minus the number of electrons. And we always write electrons with a lowercase e. I think that's because electrons have very little mass, and so they don't contribute to the atomic mass, and so we write them small. Okay, so we know from over here that P is 8. So if 0 equals 8 minus E, okay, should be pretty obvious that E equals 8. Okay, so now if I'm going to draw my little atom, I've just created not enough space for me here, so I'm going to erase this whole complicated atom that I've drawn here. And I'm going to draw it again down here. Now this time I'm going to draw it, just say P equals 8, N equals 8. And then I'm going to draw one electron shell and another electron shell. How do I know that there are 2 electron shells? Because they take 2 and then 8 and then 8, and I have more than 2, so but less than 10. So my electrons go here, here in little pairs. Okay, 1, 2, 3, 4, 5, 6. Why did I put them in those places? Just felt like it. But they pair up once you've gotten 4. Once you've got the shell half full, they start pairing up. Okay. 2 things I want to point out here. One is that once again, the number of neutrons equals the number of neutrons equals the number of protons. Okay. Does that have to be true? No. There is an oxygen 15. Okay. There is an oxygen for which N equals 7. Okay. And we write that as oxygen 15, oxygen-15, because it has the atomic weight or atomic mass 15. That is an isotope. Okay? Oxygen 15 is an isotope. It is, most isotopes other than the most common one tend to be radioactive. They tend to be unstable and they break down. Oxygen 15 is not an exception. Oxygen 15 is radioactive, and it is the reason why PET scans work. If you give a person radioactive oxygen 15, it will get used just like regular oxygen in the body, and wherever that oxygen is getting used, you'll see it light up on a positron scanner, a PET scan. Okay, so we can use PET scans to identify areas of maximum brain activity. We can use it to identify where oxygen is being used in the heart. If we're diagnosing a patient after a heart attack, we can do all sorts of interesting things with it. Okay, the other thing I want to point out is that this charge up here isn't always 0. Okay, it is possible to have oxygen -2. That's the oxide. Some atoms change their name when they become ions. Okay, nonmetals do this. That's the oxide ion. In that case, we'd have 2 extra electrons. Okay, and those 2 extra electrons would fill up the outer electron shell. Atoms are happiest, little atomic psychology here, atoms are happiest when their outer shell is full. That outer shell is called the valence. Okay, we get that from a valence in interior decorating world is actually a kind of window dressing. It's like the outermost curtain in a set of curtains. And so the outermost shell in a series of electron shells is called the valence. I guess some chemist way back when was big into interior decorating or something. All right, so now you know all the basics. Let's look at a couple of atoms and see how they behave. All right, my first two example atoms are sodium and chloride. Sodium is Na. All right, so my first two example atoms are Na and Cl, sodium and chloride. Bad chemistry joke number 2 for the day. A bunch of sodium atoms and Batman walk into a bar. The bartender looks up and says, "Nana, nana, 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 Batman." Okay. So a lot of people wonder why Na is the chemical symbol for sodium. Well, it's Latin. The Latin is natrium, and it's actually important for you to know that in biology because when we talk about a patient having too much sodium in their blood, we call it hypo or hypernatremia. Similarly, potassium is kalium, and so we talk about hyperkalemia. Okay. So sodium and chloride, I picked because they form the chemical NaCl, sodium chloride, table salt. Okay, so we're going to see how that chemical compound is formed here. Okay, so over on one side, we have sodium. Okay, sodium's periodic table square looks like this. Na. It's got the chemical number, or the atomic number 11, and it's got the atomic mass 22.99. Okay, so we know that P equals 11, and then we know that P plus N rounds up to 23. Okay, so 23 minus 11 is 12. So N equals 12. And that's good to know because that's our first atom that we've discovered today that has a normal, stable isotope with a different number of protons and neutrons. And they do happen, so that's good to know. Okay, how many electrons do we have? Well, we know that charge equals, see, there's nothing there, so charge equals 0 equals P minus E. Okay, minus because electrons are negative. So P for protons is 11. So E for electrons, in order to make this 0, has to also be 11. So we remember our 288 rule. We're going to put 2 electrons in our inner shell. We're going to put 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. In our next shell, that's 10. We have 1 more electron left, so we have to add a third shell. This is the first atom we've seen that has a third shell. Okay, so we've got 1 lonely little electron out here in the third shell. Now, is sodium happy this way? Answer is no. Sodium is not happy this way. It wants to get rid of an electron. Okay, well, it either wants to gain 7 more electrons or get rid of 1 electron. Much easier to find a lost home for 1 puppy than to pick up 7. So we're going to nix that electron, and that brings us down to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So that also means we nix this charge equation up here and we rewrite it down here. Charge equals protons is still 11 minus electrons we just counted as 10. 11 minus 10 is plus 1. Now for some reason chemists never write the 1. So we're just going to put in a positive. Okay, bad chemistry joke for the day, number 3, and I promise I'm done. A sodium atom walks into the bar and says, "Bartender, I've lost an electron." And the bartender says, "Are you sure?" And he says, "I'm positive." Okay. Now, on to chloride. Okay. So we have chlorine over here, and chlorine's periodic table square looks like this. It's got a atomic number of 17, and it's got an atomic mass of 35.45. That actually means that chloride is pretty much evenly split between atoms with an atomic mass of 35 and an atomic mass of 36. But we're still going to just round it down to get a number. Okay, so protons we know is 17. Neutrons is 34 minus 17 is also going to be 17. And again, charge equals 0 up here. So we're going to say 0 equals 17 minus E. And so E naturally equals 17. Okay, so 1, 2, 3, we're going to have 1, 2 electrons, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And see, we've got one empty spot here in our outer shell. So chlorine is not happy. Okay? It wants to have a full outer shell. So it could either lose 7 or it could find 1. You know, this time it's much easier to find 1 electron, accept an electron from sodium, say, than it is to try to donate 7 electrons. So we're now going to cross off this charge equation up there and rewrite it down here. Charge equals, this time P is 17 minus E is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 17 minus 18 is negative 1. Again, chemists never write the 1 for some reason, so we're just going to put a big old minus sign next to our chlorine. Chlorine is a nonmetal, so it changes its name when it gets an atom. It goes from chlorine to chloride. Okay. So why do these two now form a bond? Well, we have one positive over here and one negative over here, and electrical opposites attract. So these two atoms come rushing together and snap. They form a compound called NaCl, or salt. This, because it's formed by 2 ions, is called an ionic bond. Okay. Ionic bonds have one interesting property to them. When the thing is dry, if you have a dry piece of salt, you can hit it with a hammer and you can break the piece of salt into smaller and smaller crystals, but you're still gonna have salt. Okay, you can put it in a frying pan and try to heat it up and it's still gonna be salt. But you drop a piece of salt into the water and what happens? It dissolves. All the sodiums go off in one direction, all the chlorides go off in another direction, they separate. And that, because the electrical charges are separated, means sodium and chloride are also electrolytes. From the Greek lys, meaning to break apart, and electro meaning electrical charges. So the electrical charges come apart in water. So they're electrolytes. I should put in water. Okay. Fair enough? Good. Our next two example atoms are carbon and hydrogen. Let me see if I can power through those a little more quickly than I did the last two. Carbon has protons is 6, neutrons is 6. As we're starting to expect, the neutral atom has the same number of electrons and protons, so we're going to put 6. 1, 2, 3, 4, 5, 6. Hydrogen over here has proton equals 1, neutron equals 0. Not always. There are versions of hydrogen that have 1 and 2. Those are actually radioactive hydrogens. If you've heard of heavy water as a radioactive form of water, that's made with hydrogen too. Okay. So with one proton, a neutral hydrogen would have just one electron. Okay, so what do we note here? Well, there are 1, 2, 3, 4 empty spaces in carbon's outer shell. Because of the 288 rule, there's only one empty space in hydrogen's outer shell. Can hydrogen just get rid of this electron? Yes, it can. We do form H+ sometimes, which is basically a proton floating around in space, or in water, rather. But what hydrogen really likes to do with carbon is share these electrons. And so we're going to redraw this outer shell so that it overlaps with carbon's outer shell. And we're going to have one electron from hydrogen and one electron from carbon filling up that spot. Now hydrogen feels like it has 2 electrons in its outer shell, because it does. Only one of them belongs to hydrogen, but there are 2 electrons there, so hydrogen is happy. Carbon needs to form this same kind of bond with 4 more hydrogens. I mean, with 3 more hydrogens before it's happy. But now that we've plugged in 3 more hydrogens, now we've attached 4 hydrogens to this carbon, it has now formed the chemical compound CH4. Okay? These bonds, and carbon feels like it has 8 electrons in its outer shell, even though only 4 of them belong to carbon, and so carbon is happy. So everybody's happy in this molecule. Okay. Carbon hydrogen 4 is called methane. It's the main component of the natural gas that you may burn in your stove or your water heater at home. and it's the simplest form of something called a hydrocarbon, an atom of some number of carbons and the rest is hydrogen. Okay. Another hydrocarbon you're familiar with is gasoline, which typically has much larger, like 8 carbon molecules, or perhaps you're familiar with cooking oil at home. That's a lipid, but it's very similar to a hydrocarbon. So lots of molecules like this in the chemical world. Okay. These bonds, because the valence shells of the two atoms merged here at this point, this is called a covalent bond. Okay? Covalent bonds have this property. They stay together no matter what, unless you do a certain kind of chemistry to them. Okay, you can light them on fire and they will break apart. But if you drop, it's a gas, if you bubble methane through water, just like we were dropping sodium chloride in water, the methane is not going to break up. It's not an electrolyte compound. Okay, so it's going to stay together in water, which is important because the human body and all other bodies are basically 100% water. No, they're 60 to 70% water, and everything that we make in the human body that we want to stay together, we have to make with covalent bonds. All right, last topic, and I'll wrap up. How do we write these chemical structures? Let's say we had 2 carbons, and one of them was bonded to 2 oxygens, and then everything else around was hydrogens. Okay, one way we could draw this is with all those circles and overlapping, we could try to draw the electron diagram that I just drew and have a circle here and a circle here and 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 try to diagram all the electrons. That gets messy real quick. So what we're going to do instead is represent the electrons that are part of the bond only. Okay, so we can draw 2 electrons between hydrogen and carbon because they only share 2 electrons. Carbon and carbon share 2 electrons. This carbon and oxygen are actually sharing 4 electrons because oxygen needs to form 2 bonds with a partner. Why doesn't it do that with this oxygen? Because this oxygen is also forming a bond with hydrogen. So it still gets its 2 bonds. It just it's doing it with 2 different partners. Okay. Kinky, right? Yeah, okay. That gets still kind of messy to look at. So another way to write this is to draw a single line wherever there's a single pair of bonded electrons, and a double line wherever there's a double pair of bonded electrons. We call that a double bond. Okay. You can even have triple bonds between 2 neighboring atoms, but that's pretty rare. Mostly happens with nitrogen. Okay. Note that all of what I'm doing right now works for covalent molecules. Okay, covalent molecules only. For other, for ionic bonds, we just write the name of the names of the ions that are bonding. Okay, now this molecule here is perfectly fine to look at. By the way, the name of this molecule is acetic acid, which you probably know as vinegar. Okay. But what if we had an atom, what if we had a molecule that had carbon, 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 and then oxygen, and I don't know, maybe nitrogen over on this side, or maybe the nitrogen comes out here, okay, and then we have all of our hydrogens all over everywhere. Okay, you can see it's taking me a long time to write this molecule. And chemists are basically lazy, so we don't want to take a lot of time writing our molecules. Okay, so what could we do instead? Well, we know that carbon is going to form bonds with hydrogen if it doesn't form bonds with anybody else. So we can just imagine the hydrogens in. So this drawing that I did there is perfectly equal to this drawing here. Okay, those are perfectly equal structures. We just have to imagine that the hydrogens are there in structure number 2. Okay, writing all those carbons was still taking a long time though, so I could also draw it. I could also have to say, well, you know, we know carbons are going to be everywhere, so we'll just imagine the carbons in. So I'll draw this, and at every corner in the structure, that's 1, 2, 3, 4, 5, 6 corners, we have to imagine that there's a carbon there. And then I would explicitly draw in all of the non-carbon, non-hydrogen parts of the molecule. So these 3 drawings are exactly the same molecule. Here, I have to imagine my hydrogens. Here I have to imagine my carbons first, and then imagine the hydrogens. Okay. Why am I telling you this? Because in your chemistry book, in your biology book, in your medical textbooks, they will show you drawings like this right here. Just stick line drawings of molecules. If you look up the structure of some drug on Wikipedia, you're going to get a little stick line drawing like that right there. Okay, and they're going to assume that you know how to imagine the carbons and how to imagine the hydrogens. Okay. That's the end of my basic biochemistry. I hope you enjoyed it, and I hope you are ready to take the quiz on this subject and then proceed from here to the biomolecules lecture. Thank you for your attention. Have a nice day.